Welcome back. In today's lecture, I am going to talk about again the stability of equilibrium point, and our goal of today's lecture to cover the non-autonomous system. Okay, we have already seen that how to define stability of autonomous system in form of epsilon and delta. We have talked about the local stability as well as global stability. We have talked about the stability, asymptotic stability and exponential stability, and how basically they are related to each other. Okay, in today's lecture, similar kind of concept I am going to extend for non-autonomous system, and in this lecture I can only focus on two different kind of stability, that is stability and asymptotic stability. Okay, exponential stability already remains as it is. Okay, due to that reason we are just going to talk about two different kind of stability. So you can see that whenever I was talking about the non-autonomous system, so in order to make sure that this kind of equation will represent some kind of physical system, provided they have some kind of solution for some time between t0 to t1, or some compact time interval you can tell, or in the more general case I have solution for all t greater than equal to 0. So, and after that we also hope that that solution should be unique. So from the existence and uniqueness we have already seen that if vector field is piecewise continuous in T, because I have two argument here, time is extra argument, and locally Lipschitz in X, and here what I am assuming that X belongs to D and D is subset of Rn. Most of time if you see the nonlinear system, that is only defined in some limited space. Okay, so nonlinear model is not valid everywhere, that is only valid locally, and due to that reason most of time whenever we are develop some kind of theory for nonlinear system, at that time we are telling that what kind of result I can get if X belongs to D and D is subset of Rn. Okay, so what we are assuming that in this particular D, that function ftx is locally Lipschitz in X for all t that is going to lie between 0 to infinity. Okay, and one more extra assumption we are going to put here or keep here, that origin is going to lie inside this region. Okay, because I am going to talk about stability of equilibrium point or origin, so I have to make sure that origin is there. If that is not there, then how come I can talk about the stability? Okay, so if you try to understand the system, autonomous system, so I have some kind of black box, and after that I have two input channel now, because you can see that function f is explicit function of t0 and x0. So I am telling that okay, I have initial condition x0 and time t0, and then I am going to look towards the trajectory xt, and here x dot equal to ftx is going to sit here. Okay, so now my input is basically xt0 and t0, and I am going to talk about the behavior of xt. Okay, so again whenever we are going to talk about the stability, so I am going to formulate the two ball. Inside one ball my output xt is going to lie, and one ball where xt0 is going to lie. Okay, here you can see that I have explicit dependency on t0. Due to that reason I am going to tell that whatever my input ball, that is explicit function of time also. Okay, but some case it is possible to show that that is not the explicit function of time, so we will see that case. One more important point, that you can see that again in case of the autonomous system, I have already told you that without loss of generality I can transfer any non-zero equilibrium point to 0. Similar kind of situation we are going to see here in case of non-autonomous system. So first I am going to define what is meaning of equilibrium point in case of non-autonomous system. So we are telling that if ft0 for all t greater than equal to 0. If that is 0, then that is my equilibrium point. Okay, so I have system like x dot equal to ftx. Now you can keep x equal to 0 here. Okay, and if I will get x dot for all t, that is very important, because t is here explicit argument. But if you remember, in case of autonomous system, whenever I am defining the equilibrium point, at that time just we are solving this equation. Here time argument is not there. Here we are not telling that okay, fx star equal to 0 for all t greater than equal to 0. But here extra argument that comes into picture, that for all t greater than equal to 0. Okay, so definition of equilibrium point is a little bit different in the case of autonomous system and non-autonomous system. Okay, now let us try to see that why I am telling that without loss of generality I can transfer the equilibrium point of non-autonomous system to the origin. Okay, if that is not the case, then I have to separately study the stability of the origin and all other points. But it is possible to show that without loss of generality, in this case also I can transfer any non-zero equilibrium point, even if that is time varying, to the 0. So let us try to see. So what I am going to do, I am assuming that I have some kind of non-autonomous equation, and here you can see that in place of t I am telling okay, I have some kind of another time, that is tau. Okay, and this yt is the solution, this y bar t is the solution of this particular system. Okay, now what I am going to do, I am going to tell that okay, that suppose my equilibrium point is non-zero, this is y bar tau is the equilibrium point. Okay, so this is the equilibrium point, so non-zero, obviously this is not equal to 0. So what I am going to do, I am going to define some change of variable. Okay, and suppose this system is defined after tau greater than equal to a. So what kind of change I am going to introduce here, that I am going to again take y is this state, and after that y bar tau, that is my equilibrium point. Okay, and after that I am going to introduce some kind of change of time as well, because here you can see that in case of non-autonomous system, time is also extra coordinate. Okay, and vector field is explicitly depending on the time. Due to that reason, whenever I have to do some kind of transformation, at that time I have to take care of about the time also. And due to that reason, I am going to shift time by amount a, so tau minus a. Now what I am going to do, I am going to differentiate first one with respect to time. So if you differentiate, then this kind of things comes into picture, dx by dt, dy by dt, and dy bar tau by dt. This kind of things comes into picture. So you can see here that dx by dt is completely fine for me. I will define this as a x dot. But here dy by dt, I don't know what is dy by dt, and due to that reason I have to write that this is nothing but dy by d tau and d tau by dt. And similar kind of things here I will do. So for without loss of generality, I am assuming that okay, the derivative of this with respect to time I have written in form of this. Now you can see that when I have shifted the time, at that time if I will take dt, that is exactly equal to d tau, because a is some kind of constant, and due to that reason this quantity is now unity. Okay, so this quantity is unity, so dy by d tau I know that is g, t and y, and due to that reason I am going to substitute here. You can see that I have substituted here, and now tau I can, because right hand side, left hand side of this differential equation, if you see, then rate of change I have defined with respect to time. Okay, so now I have to transform everything in terms of time only, t only. Initial time is tau, so I can define the relation between t and tau like t plus a, and due to that reason this comes into picture, and y, after that you can see that y, if you see carefully, then that is x, y bar t plus a. So inside this is so this is not visible, so here you can see that here in place of y, what I am going to do now, I am going to take x and plus y bar tau. In place of tau, again I am going to replace t plus a. So due to that reason, this kind of expression comes into picture. In place of tau here, again I am going to convert into t plus a. So main motive is that now in left hand side and right hand side time argument, tau is converted into t. Okay, and everything is expressed in terms of now x, and here y bar ta, I am telling that some kind of time varying equilibrium point. Okay, something is there, I don't care about that. Okay, now since we are telling that this is the solution, y bar tau is the solution of this equation. So what is meaning of solution? If I substitute y bar tau here, then that is going to satisfy this particular differential equation, and due to that reason I can able to write this. You can see that I can able to write again, whenever I have to do change of coordinate, I will do dt by d tau equal to unity. So I can write in place of dy bar by d tau, I can able to write dy bar by dt also. Okay, and just this argument I have to change. What I am telling that initially I have dy bar by d tau. So now I am changing this, and here argument is tau. So dt and dt by d tau, and dt by d tau I know that is unity, and in place of tau I am going to substitute t plus a, and tau is here, so tau is converted into t plus a. So that kind of things I am just telling, and after that similar kind of things I am going to do here. So if you substitute this here, you can see carefully that this quantity and this quantity I have t plus a, and after that I have somehow y bar t is there. So if you substitute this quantity here, then if x equal to 0, if I substitute here, then this quantity and this quantity is exactly equal, because y bar t plus a, g t plus a, and y bar t, x is not here. So if I substitute this quantity equal to 0, then x dot equal to 0. Okay, anyone has confusion? So whenever I have to calculate equilibrium point, what basically we are doing, we are seizing the rate of change. So when rate of change equal to 0, when this quantity is exactly equal to this quantity, and when this kind of phenomena is going to happen if we substitute x equal to 0. So without loss of generality, I can tell that x equal to 0 is again the equilibrium point. Okay, anyone has confusion? So conclusion of this, that if I have non-zero equilibrium point, even if that is depending on time, that doesn't matter for us, I can transform that system to again such a way such that x equal to 0 is the equilibrium point. Now suppose if you have autonomous system and your equilibrium point is depending on the time, several times this kind of situation comes into picture, that our equilibrium point is function of the parameter, means equilibrium point is changing with respect to time. That kind of situation comes into picture. At that time, it is possible to show that even if I have autonomous system, but transformed system become non-autonomous, and again equilibrium point is x equal to 0 by same kind of transformation. Okay, anyone has confusion on this observation, then please let me know. Binay, any confusion? Okay, baby Dina?
No, sir.
Okay, Silpi?
No, sir.
Okay, so I hope that you are able to understand this point, that without loss of generality, even if I have constant point or time varying point, that doesn't matter for me. I can able to transform my equilibrium point to the origin. It means that I can select coordinate system based on my wish. That is the main motive, that is the main message from this particular transformation. Okay, now let us try to see some observation, that what is difference between autonomous system and non-autonomous system, solution of autonomous system and non-autonomous system. So again I am going to repeat example from the previous class. Here I have taken this kind of autonomous system, and this is non-linear system. You can see that here sin a square xt is basically non-linear function, and this is due to this reason this is non-linear equation, and for simplicity I am going to assume that this is just a scalar system. And what we found, that if you solve this equation, then in form of upper bound also, you can see that everywhere both time comes into picture. This is t0, that is a starting point of time of experiment, and this t is the futuristic time when I am going to see that what is behavior of my system. It means that I have provided some initial condition xt0, I have started experiment at t0, and whatever xt I receive here for this particular system, what we found that their solution is depending on the t minus t0. Okay, and it is possible to show that if any autonomous system you will take, then solution is depending, whenever solution is depending on time, at that time t minus t0 might be 0 also, that kind of term comes into picture. It means that solution is never, and this is actually the initial condition only, so solution is never explicit function of t or t0, that is depending on t minus t0 always. Okay, and due to that reason, you can see that either you can start your experiment on morning or evening, response remains the same. Why? Suppose that I have started my experiment at 5 p.m. and I am going to see the result at 7 p.m. So 5 minus 2, 5 minus 7, or 7 minus 5 is equal to 2. That comes into picture 2 here. Now, instead of this, you can start your experiment at 2 a.m. and finish at 4 a.m. Then again t minus t0, that is 2. So, if you repeat your experiment for the same time interval, whatever the starting point of experiment, your response remains the same. Okay, anyone has confusion on this observation? Then please let me know. Now let us try to see one very simple example from non-autonomous system. Okay, so here in this equation, Ankit, could you please comment why this is a non-autonomous system?
There is a time varying function there.
Yeah, time varying. So what do you think? This is linear time varying system, or linear or non-linear time varying system?
Non-linear.
Okay, why?
Sorry, it is linear, sir. Actually, it is completely multiplied with xt. That's why it is linear.
And what about this sin t?
Sin t, actually, sin t is 6t sin t minus xt is multiplying with the function xt. That's why it is linear, sir.
Okay, suppose that I have some kind of quantity, so obviously I can represent this as a at into xt. Okay. Okay, so I can write like at into xt. Okay, so now try to see the solution. Okay, so if you see the solution of this equation, then it is possible to show that solution. You can do exercise by yourself, and after that if you solve it, it is possible to show. You can see that inside the exponential I have t square, I have somewhere I have t0 square. So what happens that here in case of non-autonomous system, solution is function of t and t0, that is not only function of t minus t0. Okay, that is the difference between solution of autonomous system and non-autonomous system. Anyone has confusion on this observation? But this is not always the case, but most of time, or some classes of the non-autonomous system, solution is basically function of t0 and t explicitly. Okay, so same kind of things I have actually written here, that solution of the non-autonomous system, that is explicit depending on the initial time and t, that is not just depending on the t minus t0. And due to that reason, if you start your experiment in morning and evening, that is not remains the same. Anyone has confusion on this point? Then please let me know. Okay, now let us try to see here that as t0 t0 is my time when I have started this experiment, and t is the futuristic time. So as t is going to increase, and here everything is in form of the sin t and cos t. Here 6t plus cos t is there, so obviously this function will increase, but their rate of increment is not as faster at t square. So there exists some time t0 when finally what happens, this negative minus t square is going to dominate over t0 square. Okay, and what happens, that x t0 start decreasing from that point onward. Anyone has confusion on this point? So I can tell that whatever my solution, that solution can be represented like this, upper bounded, and ct0 means once minus t square start dominating over all the term, then what happens, this function start decreasing. Okay, so finally initially it might possible that this function will increase, because I have 6t cos t sin t, everything is there, so I have increment and after that decrement. Due to that reason there exists some kind of maxima. Anyone has confusion on this? And due to that reason, if you just substitute that maxima here ct0, then I can tell that result is going to means this kind of inequality is valid. Okay, now if you are going to formulate stability in terms of epsilon and delta, you see that whenever we are talking about epsilon delta stability, so at that time we are telling that for every epsilon greater than 0 there exists a delta that is again greater than 0. And how basically this epsilon and delta ball is connected, that first, since we are choosing the epsilon ball and that is output ball, so basically we are telling that epsilon, I need some kind of relation such that this relation will satisfy ct0, and whenever this relation will satisfy, you can see that delta I have to select, that is function of epsilon as well as t0. Okay, so I have to do this kind of calculation, then only I can able to tell that there for every epsilon there exists a delta. So what we have observed, that here this delta is function of epsilon as well as t0. But if you remember the case of autonomous system, at that time delta is just function of epsilon, not function of the initial time of experiment. Okay, so that is the difference between the stability of autonomous system and non-autonomous system for some class of system, not for all class of non-autonomous system. Anyone has confusion on this point? Iram, are you able to understand my point, what I am communicating?
Yes, sir. Sir, in this case,
Okay,
the system, the solution will not be always stable. I mean, for all t, or is it like it depends on the initial condition that we take?
yeah, actually what happens, that means solution is stable. Why? Because suppose that if you, whenever we are talking about stability, then we are making two balls, one ball about the equilibrium point, and after that another ball that is the output ball. So you can see that initially it might possible, if you start from here, your solution is going to increase. Okay, but t square is going to dominate, and after that is going to decrease, an exponential function inside t square. So finally I am going to converge to the 0 also, so that is exponentially stable. Try to see from the solution. Here you can see that minus t square is here. So suppose that if you take t 1000 second, then what happens at 1000 second, this is 6000, because cos t is going to lie between 0 to 1, minus 1 to 1, sin t going to lie between minus 1 to 1, and similar kind of a story about here also. So what happens, that minus t square is 1000 square, and t0, suppose that if you started at 50 second, so finally I have exponential minus t square. So this term, it means that right hand side is tending towards 0, and epsilon delta I can always find, because I know the maximum value initially that is going to increase, and after that is going to decrease. Okay, so I know that what is maximum value, obviously always maximum lying in terms of ct0, and due to that reason whatever fluctuation of trajectory after giving the initial condition, that is fully depending on the time. what is my initial condition. So based on that, due to that reason, that will go to upper ball, but that is not going to leave the upper ball, and due to that reason, that is stable. Anyone has confusion? Iram, are you able to understand now?
Yes, sir. Yes, sir.
And but only difference is that whatever delta ball we are going to talk, that is function of the initial condition, initial time, and epsilon. But in case of autonomous system, explicit dependency of solution is not on the time, due to that reason, or initial time, due to that reason, here for every epsilon is again output ball. Output, I have told you that how to interpret input and output. So for every epsilon there exists a delta that is greater than 0 and independent of the T0. Okay, but in case of non-autonomous system, that may or may not be depend on the T0, that depending on the system. Let us try to see the next system, then you are able to understand little more. Here you can see that again this is linear, a time varying system, and here in this particular system, again if you solve it, then your solution looks like this. Okay, and since always for all t greater than equal to T0, so you know that T0 is less than equal to T, and due to that reason, for the first moment onward, this relation is going to satisfy. Okay, so Silpi, could you please formulate epsilon and delta ball? What is epsilon ball? What is delta ball? Possible epsilon and delta ball. Silpi, are you here?
Yes, sir.
So could you please guess? I have solution. So could you please guess epsilon and delta ball?
Sir, delta is epsilon by.
How to select epsilon and delta? What is suppose that I have already told you that in autonomous non-autonomous system, this is xt0 and this is t0 and I have xt. Okay, so first which ball we are selecting?
Sir, epsilon ball.
Epsilon ball we are selecting. So here you can see that epsilon is less than and xt0 is the delta ball, because if equilibrium point is there, then we have to see distance from the equilibrium point, and after that I have, this is epsilon ball, this is delta ball. So here if I select delta equal to epsilon, that will work. Okay, or epsilon is less than equal to delta, if I will take, then that is always work. Okay, because if this is epsilon, then delta should be satisfy this kind of relation. Anyone has confusion on this? So one possible choice of epsilon delta is just epsilon equal to delta, and just because I have to select at least one, due to that reason there is no worry about the mode. Okay, so in this situation you can see that delta ball is just function of epsilon, that is not going to function of the T0. Okay, so what we found here, that in some case epsilon should be function, delta should be function of epsilon and T0 in case of non-autonomous system, or sometime it might possible that is just function of epsilon. So I have some kind of stability just like autonomous system for some class of non-autonomous system. And here could you please guess this is asymptotically stable or not? Baby Dana, by seeing solution. So we have proved that is stable, because for every epsilon there exists a delta. You can select any epsilon, that doesn't matter. So now could you please able to talk about the convergence? Baby Dana, are you here?
Yes, sir.
So this xt is going to converge or not?
Yes, sir.
As t tending towards infinity, obviously that is.
Yes, sir.
So obviously this is asymptotic stable. Okay, but one more important thing is there, that convergence time is not uniform with respect to initial time. If my initial time T0, if I am going to start experiment in morning, then time of convergence, or if I will start after 2 hours, then time of convergence, both are different. Okay, because I have to wait after T0, I have to wait some time. Suppose that if some process is completed in 10 hours. Okay, so and if I started my experiment little bit late, then time of convergence is also more, and due to that reason time of convergence is not uniform with respect to initial time. Okay, so what we found that in this case I have situation like the autonomous system, but time of convergence is not uniform with respect to initial time. And how basically we are characterizing in terms of epsilon again, that whenever we are talking about convergence time, convergence of xt to origin is equivalent to saying that given any epsilon, you can take any epsilon, there exists a t that is function of epsilon and t0 such that I can give this kind of guarantee that epsilon xt is less than epsilon for all t greater than equal to t plus t. So whenever we have to calculate the time of convergence, at that time we have to solve this kind of inequality. Okay, so this is the definition that how to calculate time of convergence, because if you are telling that xt tending towards 0 as t tending towards infinity, so quantitatively I cannot able to calculate. So equivalent definition I have to give, and equivalent definition is that you can select epsilon, any epsilon, and after that I have to solve this inequality xt less than epsilon, and we are going to see the time. So if time will come in this fashion, then I can tell that this time t is the convergence time. Okay, so in this way I am going to calculate the time of convergence. So what we found here, that two different points. One point is that whenever we are talking about the stability about the equilibrium point, at that time whatever my input ball, that is function of the output ball and plus initial time of experiment, and here initial input ball is the initial condition and time t0 we are assuming, and output ball is the futuristic xt state. Okay, so now you can see that definition. Inside the definition, what I am telling, suppose I have non-autonomous system and I have to talk about the stability of the non-autonomous system, and I am assuming that inside this region D origin is there, so that is stable if for every epsilon there exists a delta, because now it might possible my solution is going to explicitly depending on the t0 also. Due to that reason I have to allow more general definition. So this kind of definition now no longer true, that epsilon greater than 0 there exists a delta that is function of epsilon greater than 0, and then we will solve this kind of inequality. Now I have to make little more general definition, that I have to allow this delta to function of epsilon and t0, then only I can talk about the stability in the general case. Okay, so I hope that you are able to understand the motivation of this definition. Now since we have seen two different kind of example, in first example that delta is function of epsilon and t0, in second example what we found, that is just function of the epsilon, that is not function of the t0, and due to that reason now I can distinguish two different notion of stability. Okay, one stability where the input ball is function of the epsilon and t0, but it might possible there exists several class, one class of non-autonomous system where that input ball that is just function of epsilon, and due to that reason I have introduced some new notion of stability that is called uniform stability. Uniform stability means now I am not going to worry about the time, okay, but I can talk about the stability. Obviously I am not going to talk about the convergence. Okay, I am just going to concentrate on stability, because we have understood that stability and convergence both are two different quantity. Okay, and both are two different property, you can tell. Okay, so even if system is stable but not convergent, okay, or some system has both property, some system is not stable but convergent. I have actually drawn that kind of picture in previous class. It might possible trajectory leave, and after that will come to the equilibrium point. So in this case you can see that system is convergent, going to converge to the equilibrium point, but that is not stable because that is going to leave the outer ball. So I have three different kind of situation. So here what I am going to tell, that whenever we are talking about uniform stability, at that time we are telling that delta ball is just function of the epsilon. Okay, so this case is exactly similar like the autonomous case. So whenever we are talking about uniform stability or stability of autonomous system, both are exactly the same. Anyone has confusion on this point, then please let me know. So I can tell that some class of non-autonomous system has similar behavior like an autonomous system, and if that is the case, then system is uniformly stable. And we know that definition of instability or unstability is that if something is not stable, means I can not able to formulate epsilon and delta ball, then system is called unstable. And now again come to the asymptotic stability. So asymptotic stability, again I have similar kind of situation like the autonomous case, system should be stable, and after that there exists a C, and C is function of t0 greater than 0, such that if my initial condition inside this C, then if I will converge xt tending towards 0 as t tending towards infinity, and I have already told you that how to check this convergence, that that is uniform or not, by solving that inequality. You can take epsilon ball xt and you can solve xt less than epsilon and then find the t plus t0. Okay, so if these two conditions is satisfied, then we will tell that system is asymptotically stable. And locally, because you can see that there exists a C is function of t0 greater than 0, we are telling, and initial condition is going to lie inside this. So I am not going to tell that for any initial condition this kind of phenomena is going to occur, and due to that reason this stability is local stability. But if this kind of, if I allow initial condition to any value, then that is called the global. We will see that point. And after that uniformly asymptotically stable, at that time whatever C, that is not going to depend on the t0. You can see that what is difference between these two. Here whatever input ball I have selected, this ball, here C is there and C is function, explicit function of t0, so that is depending on the time of experiment. But if that is not depending on the time of experiment, then we are going to talk about uniform asymptotic stability. Same like stability, uniform stability, now we are going to talk about asymptotic stability and uniform asymptotic stability. So in order to talk about uniform asymptotic stability, first I have to make sure that system is uniformly stable. Means for every epsilon there exists a delta, and delta is just function of epsilon, that is not function of the time of experiment t0. And whatever input ball now I am going to select for convergence, that is not going to depend on the t0, means I can take any C independent of t0. If this kind of condition is satisfied, then I can tell that my system is uniformly asymptotically stable. And in other language I have told you that whenever we have to calculate the time of convergence, at that time we have to solve like this. For eta you can take any eta and take some kind of time, that is function of eta. So if you solve this inequality, and if this kind of things comes into picture, for all xt less than equal to C, then we are telling that system is uniformly convergent, like that. So this is the numerical way to test the convergence. This way xt tending towards 0 as t tending towards infinity, we have to wait for very large time. But suppose if you are going to write some kind of numerical algorithm to test uniform stability, at that time you have to write like this. Due to that reason, whenever we are giving some kind of definition where infinity is involved, at that time parallelly we have to tell some definition in terms of the some kind of finite number also. And similarly global uniformly asymptotically stable, if that is uniformly stable, now whatever this delta epsilon I am going to choose, that is infinity. Okay, it means that my initial condition is going to lie anywhere, that doesn't matter for me. Okay, and after that what we have to make sure that this time of convergence, now that is not only function of one value eta, that is function of C, because now what I am telling that any ball of initial condition I will tell, corresponding to that ball I have some convergence time t. And if you solve this kind of inequality, and if this inequality will satisfy for all t0 plus t eta C, then we are telling that my system is globally uniformly asymptotically stable. No system. So what is the story? story is in this form, that solution of non-autonomous system for several classes of nonlinear system, nonlinear non-autonomous system, is explicitly depending on T0 and T. And due to that reason, whenever we are talking about the epsilon delta stability, at that time, whatever delta ball, that should be function of epsilon as well as T0. And due to that reason, we have two different form of stability. That is, one stability is simple and another is uniform stability, uniform asymptotic stability, uniform stability, that is just like the autonomous case. Okay, in the next part of this course, we are going to see more transparent definition of the stability of non-autonomous system in form of K and KL class function. Okay, that is very convenient to work. In this way, you can see that working with this definition is not so much convenient, and due to that reason, in later part, people has introduced new definition that I am not going to cover at this moment. So that is, they have defined some function K or KL class function, and in that form we are going to talk about the stability of autonomous system as well as non-autonomous system, and then we are going to talk about input output stability. So that is the story of next part of this course. Okay, now this class is over from my side. So if you have any question, then please let me know. Anyone? So are you able to understand the difference between stability of autonomous system and non-autonomous system? Ankit, do you have any confusion?
No, sir.
Okay. So, and baby Dana,
Yes, sir.
do you have any confusion? Are you able to distinguish between these two cases or not? Means case of autonomous system and non-autonomous system.
Yes, sir. But sir, can you please explain one more time about the uniform assistant, how to choose eta and all that
Okay.
last one?
Okay, I will again define this. Okay. Come to this example. Okay, here this example. So whenever we are talking about stability, epsilon and delta stability, then what is first step, baby Dana?
Yes, sir.
What is first step? We have to solve equation. Okay, so if I have one dimensional equation, then solution is pretty easy. Suppose if you have higher dimensional, then what you have to do? You have to apply comparison lemma. Okay, and comparison, what is beauty of comparison lemma? Again, you can able to get solution in form of ball only. Directly in form of ball, you are able to get the solution. Okay, once you will get the solution or estimate of the solution, at that time what you have to do? You have to see the whatever solution with us. Okay, and after that we are going to look that, because we know that xt, whatever ball of xt, that is epsilon, xt0, that is delta. Apart from that, we have to look towards the term. Okay, and that term is basically responsible for the ct0. Okay, or some kind of quantity that is depending on the time. Okay, so and after that what happens, that if I fix delta, if I fix epsilon, and this term is somehow depending on time 0 t0, and how basically I can define that term? If we have function, then we will plot it. Okay, so if I plot, then I am able to get some kind of maxima. If that will not exist, it might possible something is always increasing. So if something is always increasing, then that is unstable. Okay, that is no longer stable. So if delta, that is function of epsilon and t0, then I am telling that system is stable but not uniformly stable. Okay, but suppose after solving the equation, this t0, explicit dependency of t0, that doesn't come into picture, then what kind of conclusion I can tell? I can tell that, okay, since delta is just function of epsilon, so if that is just function of epsilon, then that is uniformly stable. Let us take one example, then things become, I think that things become little more clear to you. So I will take the example of linear system x dot equal to at into xt. Okay, and if you see the solution of this, then and you can take very general case, xt belongs to Rn. So I can able to write solution of this equation like phi t t0, and this is a state transition matrix, and xt0. Okay, now you can see that I can also able to write this like from this is called norm inequality. So if I apply norm on both sides, so norm of this quantity is exactly equal to this quantity. After that, AB norm of this quantity is less than norm of A and norm of B. Like that I have done. Okay, baby Dana, do you have confusion on this inequality?
No, sir.
Okay, now you can see here that I have two different balls, and one ball I have defined one ball like this. One ball I have and without loss of generality, we have seen here x equal to 0 is my equilibrium point. So I have actually formed one ball xt minus 0, that is equal to that is less than delta, you can see. And now by substituting this, and I have another ball less than 0, sorry, this should be epsilon, and this is delta. Okay, now what happens that if I substitute delta epsilon here, then I have this kind of relation t0, and after that I have this as a delta. So you can see that delta is somehow, I have to select delta that will satisfy this kind of relation, and this is a scalar quantity. Due to that reason I can write in denominator also. Now depending on this term, I can tell that system is uniformly stable or not uniformly stable. Okay, so suppose that if this term phi t0 is bounded by some kind of constant quantity c for all t and t0, then what happens? What I can tell? That delta is depending on t0 or not? Baby Dana,
Sir.
are you able to understand my question?
Yes.
What I am
Delta
telling?
depend-
Yeah, so in this case you can see that I have this kind of relation. Okay, so if we are able to make sure that for all t or t0 this is just less than some constant quantity, then at that time my original system is uniformly stable. Okay, but suppose if this is bounded by some kind of quantity t minus t0, that is less than ct0, okay, or ct0, I have to write ct0. So at this time you can see that delta should be satisfy this kind of relation. Okay, it means that depending on the time of experiment I have to select different value of delta, but that is not the case here. Okay, in this way I can able to distinguish two different kind of stability, even if in case of linear, even if in linear case that I have uniform stability or I have just stability. Are you able to understand my point or not? Not, baby
Yes,
Dana?
sir. Yes, sir.
Now, whenever you have to talk about the convergence, at that time I have told you that how basically I will talk about the convergence. At that time we are telling that I have some kind of epsilon, so xt should be some kind of epsilon, so epsilon should be less than phi t0 and xt0. Now what we have to see, we have to carefully see that when this relation will satisfy. So for corresponding to that, it is possible to show that there exists some kind of time t0 and plus, and whatever time I am going to consider, that is function of epsilon, obviously, because that is depending, if I select larger output, so corresponding to that there exists this kind of thing. So by solving this I can pick this time t, and this time is, now you can see again that it might possible this time t is function of epsilon, sometime this is function of epsilon and t0. So if that is just function of epsilon, then I can tell that I have a uniform. If that is function of epsilon and t0, then that is not uniform. In this way one can able to conclude. Okay, any confusion?
Sorry sir, not audible.
What I am telling that now if you have to calculate the convergence time, okay, so how to calculate the convergence time? You have to check that when this inequality will satisfy. Always this inequality means if you select some epsilon value, suppose if you will take 10, so 10 you have to solve this equation, and suppose initial condition is 2. At that time, now you have to see that when phi t0 is 5 should be less than equal to phi t minus t0. So this inequality will satisfy after some time. So t0 is time of experiment when you have started, and after that you have to check that how much extra time if I will wait such that this inequality will satisfy. In that way I can able to calculate the time of convergence t.
Got it sir.
Okay, so thank you.
Thank you sir.
Any other question? Okay, if you don't have any question, then I am going to close the today's lecture because we have next lecture also. Okay, so thank you very much.